All right, guys, so one last lesson on systems of equations for the week to get you through the week here. And this one's fairly short, but it's kind of an important topic with systems of equations, and it has to do with the number of possible solutions to a system of equations. So to introduce this topic, I'll give you a couple of word problems. You could solve them in pictures. I don't know what your jam is here. But let's say yesterday I go out and buy 6 cheeseburgers and 3 fries and I spend $18. So we'll say cheeseburgers are X and we'll say fries are Y. So 6X plus 3Y equals 18. And then today, I bought 2 cheeseburgers and 1 fry for $6. So 2X plus Y equals 6. So how much did the cheeseburgers and fries cost, and do I have enough information to say? Well, if I were trying to solve this as a picture problem, what I might do is maybe take today's order. And with today's order, I noticed that I bought 2 cheeseburgers, and yesterday I bought 6. So maybe if I can multiply today's order times 3, I can get up to the same number of cheeseburgers and then solve this by elimination. So I'm going to do that. I'll take that second equation and multiply it times 3. So I'll copy the first equation, same as before, 6x plus 3y equals 18. And then the second equation, if I multiply both sides by 3, I'm hitting the wrong button here, I get 6x plus 3y equals 18. So that's interesting, because then if I try to, solve this by elimination and I subtract one equation from the other, 6x minus 6x is 0, 3y minus 3y is 0, and 18 minus 18 is 0. I mean, of course, 0 is equal to 0. Like, what else would it be? But it doesn't seem like I have enough information to be able to actually say how much these things cost. So we could go through this using another strategy like substitution, but let's maybe check this with graphing just to see what's going on there. So I'm going to go over to another tab, and I'm going to go to Desmos to do graphing. So desmos.com. And let's put both of those plots into Desmos. So we've got 6x plus 2, I can't remember how many fries it was. Hold on. 3y equals 18. Okay, next we've got 2x plus y equals 6. So I graphed both of those lines, and oddly, those lines are the same line. My red line and my blue line completely overlap each other. So, the answer is, of course, the cheeseburgers could cost nothing and the fries could cost $6, or the cheeseburgers could cost $3 and the fries could be free, or it could be somewhere in between. Like in this situation, they could each cost $2 and I would still get the same answer. $2 for cheeseburgers and $2 for fries would still equal those same amounts. So I do know that the prices for those things have to lie on this line, but I don't have enough information to tell exactly where on the line it is. So it's a special kind of system where both of these equations are actually the same equation. They just didn't look like it at first. Let's take a look at another situation along the same vein. So yesterday I bought 6 cupcakes and 5 cookies for $42. Today I bought 12 cupcakes and 10 cookies for $50. How much do cupcakes and cookies cost, and do I have enough information to say? All right, so we'll write this as 2 equations. Let's say cupcakes are X and cookies are Y. 6X plus 5Y equals 42. And then next situation, 12X plus 10Y equals 50. Now, if I were solving this with elimination, I might take this whole equation and double it, and then that would enable me to subtract the 2 equations and figure out how much the cost is. So let's do that. We'll double the first equation. 12x plus 10y equals 84, and then next equation down is 12x plus 10y, interesting, equals 50. And then if I subtract those 2 equations from each other, 12x minus 12x is 0. 10y minus 10y is 0. 84 minus 50 is 34. So in this situation, we ended up with 0 equal to 34, which is weird. Trying to solve it algebraically ended up with this like impossible situation. If I go to Desmos and I try to graph these equations, look and see what happens. So I'm going to get rid of my drawing and we'll go over to Desmos. I'm going to keep my other equations up there just so I can use them to make a point. So we've got, I have to remember what the equations were. Hold on. 6x plus 5y equals 42. And then in the next situation, we have 12x plus 10y equals 50. Okay, so we're looking here at the green and the purple lines. And what's weird about the greens and the purple lines is normally when you're solving a system of equation, you look to see where those lines cross. And those two lines, as far as I can tell, are perfectly parallel. They don't cross anywhere. So they refer to like a completely different set of prices for cupcakes and cookies. On the green line, cupcakes and cookies cost one thing together. And on the purple line, they cost something completely different. And so there really isn't any way that there's any combination of those two prices that would be on the same line at the same time. In the situation like the first one with these, cheeseburgers and French fries, there's an infinite number of ways that you can combine those prices and still end up with solving the system. So those two together have an infinite number of solutions. The green and the purple lines are parallel and never intersecting. There's no possible way you can come up with any set of values that's on both lines at the same time. There are 0 solutions. So there's 3 possible configurations for systems of equations. You can have one solution where the lines cross in one place, an infinite number of solutions where they're basically the same line, or you can have no solutions where your two equations are parallel lines that never cross. How do you tell the difference between those, and when do you know if you should go through the process of solving them? Well, as we noticed before, when we tried to solve this first equation algebraically, we ended up in a situation where we found a statement that was always true. We came up with 0 equals 0. And so in that situation, there's an infinite number of ways that 0 can equal 0. Infinite solutions if you end up with an answer that's like, duh, it's always true. If you end up in a situation where you've got an impossible statement, so something that's always false and there's nothing you can do to make it true, then there are 0 solutions. So if it's always true, there's an infinite number of solutions. If it's something that's never true, there are 0 solutions. Let's take a look at a couple of these examples just to illustrate that. So in this first example here, so we've got 6x plus 2y equals -6 and 7x plus 4y equals 8. I'm looking here and just think with my elimination hat on, this 2y is half of the 4y, so I'm going to double the first equation. So that gets me, I'm going to stop drawing and use the text here. That gets me, oh, never mind, I'm going to draw after all. 12x plus 4y equals -12. And then 7x plus 4y equals 8. So if I subtract these two, 12x minus 7x is 5x, 4y minus 4y is 0, and 12 minus 8, or sorry, -12 minus 8 is -20. I haven't finished solving this, but this is going to get me to a place where there's one solution, because I'm coming down here to one possible value for x. This is possible to solve algebraically. And if I graph it, I'm going to find that I have 2 lines that cross in one place. Let's take a look at this one. 5x plus 3y equals 15. 10x plus 6y equals 20. So once again, I noticed that between this 3y and the 6y, I could double the first equation, and I could solve it by elimination. So I'm going to double the first equation. 10x plus 6y equals 30. And then the second equation, 10x plus 6y equals 20. So I'm going to subtract those two and try to solve this using elimination. That's supposed to be an x, and that's a y. So if I subtract 10x minus 10x, that's 0. Subtract 6y minus 6y, that's 0. Subtract 30 minus 20, that's 10. 0 is not equal to 10. That's a false statement. We end up in this situation where we've got an impossible statement to resolve. And so this is a case where we've got two parallel lines. They're never going to intersect. There are no solutions to this system. Okay, third situation. Negative 6x minus 9y equals 0, and negative 24x equals 36y. This one seems like a good candidate to solve by substitution, because in the second equation, I can really easily get an x equals y type of relationship there. All I have to do is divide both sides by negative 24. Okay, so negative 24 and then negative 24. That means x is equal to negative 1.5y. I'm sorry about my bad handwriting. So I'm going to take negative 1.5y and I'm going to plug it into the first equation in place of x. So negative 6 times negative 1.5y minus 9y equals 0. Okay, so far so good. Negative 6 times negative 1.5 is 9. So 9y minus 9y equals 0. And so then in this situation, I end up with 0 equals 0. And this is another curious, algebraic problem to have. 0 equals 0 is true. That's like a duh. It's always true. It suggests to me that even though it may not look like it, this first equation and that second equation are actually probably the same line. And so there's an infinite number of solutions. And just to make sure of it, let's go back to Desmos and check it. So negative 6 minus 9y equals 0. Let me get rid of these and check it out. Okay, negative 6 minus 9y equals 0. That's supposed to be an x. Yes. And then the next one was 24x equals negative 36y. And yes, in fact, the red line perfectly overlaps the black line. Those two equations are the same line. So in this situation, problem number 11, there's an infinite number of solutions. So just to summarize, if you work through working a system of equation and you get one clean answer, there's one solution to that system. If you work through a system using substitution or elimination and you end up with a statement that's always false, there are 0 solutions. And if you work through it using substitution or elimination and you end up with a statement that's always true, then there's infinitely many solutions. And you can check your work by graphing. 0 solutions have 2 parallel lines. Infinitely many solutions have the same line. On Khan Academy, you'll see there's a practice set of problems that go through the same concept, and all you have to do is pick the number of solutions to the system. Okay? Good luck. That ends math for the week, and so we'll pick it up again next week for our final week of this session.